Okay, so what I'm going to do today is continue where we left off, and we'll look at two case studies essentially. We'll look at DQN as well as AlphaGo Lee, AlphaGo, which beat which was from 2016. So I think they use the phrase AlphaGo Lee to refer to that version. So we're going to look at that particular version. Okay. And the current video I'm just displaying is an example of what deep learning plus RL, although it may not be RL here, plus RL can do in terms of directly talking about decisions, which is in this case controls, rather than just focusing on prediction problems. So with that, let me share my notebook. Okay. Okay. So as I said earlier, actually, let me just recap some of the goals for today. Okay, maybe I should share that window. Okay, so last time we were looking at basics of reinforcement learning. Last two lectures ago, we were talking about basics of reinforcement learning, and last lecture we looked at the Q-learning algorithm as an approximation to, which takes into account, it starts from Bellman optimality equation and then makes a few, changes essentially. That's one way to interpret how we got to a Q-learning algorithm, particularly the update step. So today's the objective is to, we'll quickly recap that Q-learning algorithm, and then we'll talk about the role of function approximation. And that's where, you can bring the power of the things that we saw in the first 6 or 7 lectures, which is basically deep learning architectures. So we'll talk about function approximation in the context of Q-learning, and we'll be able to look at a particular instance of that, which is called DQ network. So, and maybe during that discussion, I'll briefly allude to that. You don't have to really just approximate value functions. Q function is just a state action value function. You could also approximate directly the policy function. So there are policy based, there are algorithms which directly optimize the policy instead of thinking about value functions or state action value functions. Okay. But we haven't touched that in the previous few lectures, and neither are we going to touch that today. But maybe when, at the appropriate times, I'll just refer to them. If you're interested, you can read them. Next, the second part of this lecture, we're going to look at not so much as an RL problem, but in the context of playing Go, we're going to look at a very interesting algorithmic technique called Monte Carlo tree search. So it's a search algorithm. So it actually belongs to, I guess, the class of problems that are related to planning. So recall that in planning problem, your objective is to not learn, but you may already have a model of the environment or whatever, but your objective is to just plan. Okay, and plan just means, again, to produce a policy, but in this case, you probably know the environment. In this case, for example, when we talk about Go, we know exactly, when you make a move, what's going to be the next state. Okay, like when we were talking about chess last time, I think when you make a move, you know exactly what's going to happen in the next time step. But even knowing that, you may not be able to figure out the best move. And so there are some ways to do that. And one of the techniques is called Monte Carlo tree search. Okay, and we'll look at that, and we'll see what's the difference between Monte Carlo tree search. What is this new thing called tree search? And we'll contrast that with a very more, I guess, intuitive technique called Monte Carlo search or Monte Carlo rollouts. Okay. And then as a case study, we're going to look at AlphaGo, the 2016 version. So that had a couple of, uses of deep learning, as in deep neural networks, in conjunction with this Monte Carlo tree search technique. Okay. So we'll look at two instances of deep learning. One in the context of Q learning while playing video games. And second, in the context of Monte Carlo tree search, again, we are looking at the game of Go as an example, but we'll look at how deep learning is also used within the algorithm there, which is called Monte Carlo tree search. It's something different from, I guess, Q learning. So those are basically the two algorithms that we are looking at pretty much. So in throughout this previous few lectures of talking about since we started RL, only last lecture or last session we discussed one algorithm that actually learns a good policy. Okay, it does learning, right? So that was Q learning. Today we're going to continue talking about Q learning with deep learning, and then we'll look at another algorithm. It doesn't replace Q learning itself, but it is in a slightly different context, which is in the context of planning. Okay, so that's the goal. So those are the 4 goals. So let me go back. So any questions about the layouts and end? Okay, so if not, we'll start with the first part. And in fact, I'm going to recap Q learning again, just to kind of at least, so that we can at least recall the Q learning update step. It's a, and you'll see that in contrast to supervised learning, where we just specified a model, when we talked about the first, like a CNN based function, CNN based classifier and things like that, we specified a model. And then we didn't pay too much attention to, so loss functions are sure, there's cross entropy loss function and so on, but there was no explicit discussion of an algorithm, right? So there the algorithm would be a standard, if the model was differentiable, then you just use stochastic gradient descent or variations like that, and you have used certain optimizers in your previous assignments, right? So there was not so much emphasis on algorithm, although algorithm is essentially equivalent to optimization. What is the way in which you're going to optimize your model? We didn't spend much time there. Maybe in a couple of lectures, we're going to talk about those options, about optimizers when we get back to deep learning. But here you can see that Q learning was a canonical, or at least the first algorithm that we saw, which had some, which was different from supervised learning, and was giving us this policy function, right? A mapping from state to actions. And it was computed using these intermediate representations or intermediate objects called like state action value functions. Okay, state action value function, or a state action value function matrix. Okay, so that's the, I guess, a difference from, there's some emphasis on algorithms in this set of techniques that you're seeing in the past couple of lectures in RL. Whereas there is of course an emphasis on algorithms even in supervised learning, but it's there are some standard algorithms using gradient based methods like SGD or ADAM or RMS prop and so on. So but we'll maybe visit those algorithms or optimization schemes a couple of lectures from now. So just to recap, what's Q learning? So before that, let me just cut this out and say Q value iteration. Okay, because I'm going to show you what's the, so we'll start with basically a Bellman optimality equation and turn it into an iterative update. Okay, so Q value iteration, the way it's different from Q learning is basically Q value iteration assumes access to the model. Recall what is the model? It's this probability of going from S to S prime given A. Okay, so I mean, if you're in state S and you take an action A, what's the, with some probability it'll go to state S prime. So this is a part of the model. And similarly, you would also need the reward function if you're in state S and you take action A, what's the reward you're going to get? Okay. So that's the model. So if you already have access to the model, what you would do is basically what is one of the algorithms is called value iteration. And if you do, you can do value iteration with just the state value functions, which is, recall state value functions were just functions of the state. For each state, there would be a number which says how good the state is. But this Q value iteration is just a value iteration which uses the state action value functions. Okay. So you start with the Bellman optimality equation, and that optimality equation is what's written at the bottom here, which I've underlined. You start with that and somehow turn it into an iterative update. Okay, and how do you do that? This is all intuition, although this can be made rigorous, and mathematicians have figured out how to say that this iterative update actually gets us the true, the best state action value function values, right? So what's the iterative update? Since we have the Bellman optimality equation, what we're going to do is change this equality to an assignment, right? Where we start with some initial values, okay, some random numbers, and keep computing the left-hand side, right? So it will be basically Q old, that's the Q. Yeah. So do a for loop where you start with some random numbers for this Q star, or some instead of Q star, you can just call it Q if you want. Start with some older random values of Q, and then you keep updating because you have the model, you know exactly these intermediate quantities, you know exactly how to take a max, given any state. So you keep updating the um, um, uh, you compute the right hand side and update the left hand side, then use the left hand side as new numbers, and again compute the left hand, again compute the right hand side, and so on. So this should be clear, right? So for loop, new is computed using old, and then basically the old becomes is new, okay, for the next loop. So this is the for loop, 2 steps. And if you do that, that's Q value iteration. So given Q value iteration, the intuition behind Q value iteration, which is this changing of an equality to an assignment and doing a for loop, iterative update, Q learning algorithm does a couple of more changes, okay? And those changes are necessary because, first of all, we don't have access to the model, right? So no access to model. No access to model. So you want to deal with how do we get away from not having a model? We're going to do basically sampling, which means that we're not going to take an expectation here. So if you look at this is an expectation operation, an averaging operation. Instead of an averaging operation, we're just going to take one sample, okay, essentially. And second thing we're going to do is in Q value iteration, actually. So I forgot to mention here, Q value iteration, you're going to do this for loop from, compute new values from old values for all state action pairs, okay? So, I mean, you're going to do, so think of the Q matrix, right? So it's like saying, I have this Q matrix, Q new matrix. I'm going to compute this full matrix using this old matrix. Okay. Full matrix in the sense I'm going to compute the first value. I'm also going to compute the second value, also compute the third value, and so on, all at the same time. Okay. So I'm computing for everybody once, and then repeating the step again and again in a for loop. Okay. Whereas we're going to do it in an incremental way. So we're not going to compute. So we're not going to compute the new Q values using old values for all state action pairs, because we are going to be learning in an environment, for example, using a simulator or in the real world. And we can't just jump from, state S1, A1 to state, S10, A10 arbitrarily, right? Unless you actually took an action and because of the environment, you ended up in state 10, you can't get there. So you have to do incremental update. So basically you update one entry. It's like basically one entry in the Q matrix. Okay. And then there's also this need for exploration, and that was something that we recognized starting from when we were talking about the general online machine learning loop, right? When we looked at multi-on bandits, when we look at contextual bandits, we needed exploration. Okay, so which means that you can't just rely on past data; you have to try something out. Okay, because of this data, because you may be missing out things that you didn't try, because their estimates are off. You were unlucky initially, and the estimates were off, and so on. Okay, so if you want to revisit this, just look up epsilon greedy algorithm for multi-on bandits. And in fact, even for Q learning, we essentially do epsilon greedy. So just look up why and think about why we need that. Okay, so with these three changes, basically, which just means that equality anyway, when we talked about value iteration, it gets changed. Instead of this averaging, we're going to do sampling, and we're going to do an incremental update, and we're going to do exploration. Exploration doesn't really enter directly. Maybe I'm going to talk about it, but you can, in this update, you will not see the exploration. But when you actually look at the Q learning algorithm, when you take an action, that action you take with some probability the best action so far, which is using a max operation on your current queue table, and you take a random action otherwise. Okay, so what is this diagram in between? So this is the diagram that's been consistently being shown in each of the slides. It's basically how Q star is related to Q star of some other state action pair. Okay, so this is just the diagram which accompanies the Bellman optimality equation, where Q star of S comma A is related to, okay, from S comma A with some reward, I'll get to some S prime or S double prime or whatever. And from there, if there's an action one, action two, action one, action two, I'll get to 4 new state action pairs. And for each of those state action pairs, there's going to be a corresponding Q value. And that Q value is related to the first Q value using that equality. Okay, that's what this diagram is showing. And to talk about the sampling business, we just dropped, it's a very similar thing from a state action pair. Instead of looking at a branching like this, because, that would be all possible future states you can get to and all possible future state action values that you can get to. Here, you're looking at only one path over there. So given a state action pair, from one path, you may get to one of the states as prime. And at one of the states, you have to take an action A prime. So here's the update rule. So this update rule is basically saying, take the old value and, this update rule is basically the same as 1 minus alpha, some previous values times old plus alpha times basically r plus gamma q of s prime a prime. Now what's now decided is what is this a prime, right? So we need the a prime, and that, just to go back to our Bellman optimality equation, that a prime choice was basically pick the a prime, which is basically equal to max over so given my current queue table so far, what's the best action that you can take? Okay, so this is basically if you just start from Bellman optimality equation, this is what you would get. But there's an intuition. There's an intuition because you could choose a different a prime. There's some choice here because you could have chosen a prime based on my q old values. Sorry, you could choose the a prime again based on epsilon greedy, right? You could have chosen that, but this is not something that we do, and so these two slides are just saying that. Okay, so this is the Q learning update, which is what we saw in our algorithm. Basically, take the old value plus add to it an alpha times what is called a TD error. Okay, and it's actually called TD0 error, but it's fine. So we'll just call it TD error. So you do this update. So now let's come back to our algorithm. So the algorithm is start with some, think of a Q matrix, state cross action matrix. Start with some arbitrary numbers. Let's say there's always some starting state. Maybe, for example, when you play a maze game, you always start with the start position. Let's say that's the state 1. And then for every time step in an episode, you take an action. So these 2 steps are basically take an action either greedily, which is this part, or you take it arbitrarily, which is the exploration part. So this part is just saying pick an action 80. Once you pick an action 80 and play it, you're going to get the current reward, which is RT plus 1. You also get the information about the next state. Okay. Now with those 4 numbers, which is with those 4 numbers, which is current state, what action you took, what's the reward you got, and what's the next state you went, you can do this update. And this is an incremental update. It only affects, you're only going to update the state action pair that you were involved with at the current time steps, and not the whole Q matrix. And that's it. You keep doing this over and over again. And in theory, this should actually, at least in the matrix case, and this is actually called the tabular case. Okay, it's a table. For the tabular case, it's actually people can show that in the limit you actually get to the best state action value function. Okay, so you have actually optimized. Remember, the star represents the max over all policies of Q of S comma A. Okay, so no, I should not write A. That's okay. That's right. A. So say R max is equal to Q star. Okay, so optimize. So this is the best state action value function you can get if you, if you could pick the best policy among all policies that you can consider. Okay. Um, so, and I think I was pointing out last time that this equation needs a little bit of more nuance because this left-hand side is essentially a random variable. So the Q matrix is a random variable because if your environment is random, so these numbers are changing, and so um, um, you want to say something a little bit more nuanced here. Okay, so it's not a big deal, but it's just a technical point I wanted to point out. But that's Q learning algorithm. Any questions about this part? Okay, if there are no questions, then so what did I do in the past 5 minutes or 10 minutes is basically start with Bellman optimality equation and then talk about Q value iteration as an intermediate step to kind of motivate the Q learning update step. Okay, this is the most important thing. And Q learning is quite straightforward, at least intuitive. It's basically get you take an action, you do incorporate exploration, and then you do an update on this Q table. Okay, and this is called Q learning or tabular Q learning. And from now on, we're going to talk about function approximation, and we'll see that why this is not enough. Okay, and this algorithm needs changes to actually work in more realistic settings. Okay, and that is illustrated using this diagram here. So let's say a robotic agent. Let's say this one. Okay, and it needs to get to this door here. Okay, if you have a way to, let's say, if your environment is represented using this left-hand side figure, which means that it's essentially a grid, at XY plane, and you have XY positions, and and you can see the position of the robot as this green dot here. And if states are just positions in a grid, and let's say you have a bunch of actions and a bunch of rewards, then you can see you can create a table, right? You can create a table where you will have the 4 actions, so forward, backward, left, and right, and each of the rows will be a position. Okay, so yeah, there are maybe lots of positions, maybe 500 of them. So you can create a table, but that's quite limiting, right? So what if your input is actually in the real world, you'll actually get a camera view, and you saw that when I quickly, when I showed um, uh, the self-driving demo by Tesla. So you would have camera views, right? So that would be your measurement, that would be your measurements or sensing modality. Then what you see is actually what you see is on the right side. This is not what you see. Okay. So given what you see on the right side, how do you maintain a Q table, right? It's very hard, right? So what would be each state be? Each state, if you think of an image, the image has so many pixels and so many, let's say 3 channels. You cannot make an entry for every possible image that the camera is going to sense. Okay, so you'll run out of space. Okay, so to fix that, people have figured out that we don't have to think of a table version of Q or the state action value function. We can actually approximate because state action value function is just a function of state and action. So we can actually introduce a parameter, some parameter. So okay, so instead of this, we're going to make it Q s comma a with some parameter w. Okay, and I'm using w because that's you'll see that it's basically will approximate using a neural network. Okay, so we can use any function, any function, okay, for any function class to restrict which class the Q state action value function belongs to, and then we can just figure out its parameter. Okay, so but such a function approximation choice of we can approximate such a function approximation idea need not just apply to the state action value function. I can do function approximation to just the value function if needed. So v of s, I can change it to v of s with some parameter theta or w. And even policy, instead of saying policy pi of s given action, I can say this is also parameterized by some parameter theta. or the model itself could be P of S, it's basically S prime given S comma A at given parameter theta. So this is just extra parameters. I'm just saying that you can characterize all these three quantities using functions. Okay, so that would be function approximation. Without this extra theta, it would be, you haven't approximated your any of your objects. Okay? If you can do function approximation, so let's say you use something, maybe a function class, maybe a linear function, in which case, for example, q of s comma a given w would be something like w transpose. Let's call it features that depend on s comma a. Or it could be just be is equal to w transpose s and a. So this would be a linear function, right? So this is a linear function because its parameter is a linear parameter, w. So if you have something like this, okay, some function class, maybe a deep network or a linear function, then you can optimize this function end to end in the sense that somehow, you need to change. I mean, we will do that. We need to just change the Q-learning update step. And once we do that, then we can actually optimize, we just need to change the update step so that we change the parameter, okay, every round or every iteration, whenever we choose to update it, we're going to change W instead of the Q at a specific state and action pair. Okay, so and this can be done if as long as the approximator is differentiable. Even if it's not differentiable, we know how to update parameters. For example, with we have done it with boosting and addition trees. For example, the trees themselves are not differentiable, but we got around that using some tricks. So yeah, and if it's differentiable, then you can just use SCD, Atom, whatever you want to use there. Okay, and we can do this update optimization, incrementally or in a batch mode. Okay, so this is something that we have not seen in Q learning. We were doing things incrementally. Okay, which is at a given state and a given action, we would get a reward in the next state. Given those, that 4 tuple objects, we would just update the Q value, so we can change that into a batch mode as needed. Okay. And we're gonna, okay, I guess we can discuss about batch mode as we move forward. So let's talk about how we're going to store, right? So instead of storing, so basically in the tabular Q learning case, the simple algorithm that we saw towards the end of last lecture and recap today, instead of storing, so we were storing a table, basically a table with states as rows and actions as columns. So instead of that, we need to find some scalable ways to capture the Q values. And, the way we're going to, we just discussed that we can represent the Q function as a Q using a function approximator with some weights or parameters W. And what we're going to do is, we can have two representations, okay, two types of representations, just an alternative. So one straightforward one is what's written here. So you could have state and action as an input, and you can have Q value as a Q value at that state and action as output. But an alternative way, which is going to be convenient for us, and there's no difference between the left side, figure 1 and figure 2. What's going to be convenient for us is just to give state as an input and produce the Q value at both at action 1 and action, at all the actions that are available at that state. Okay, so yeah. Yeah, so basically it just becomes think of this as, if you think of, if you go back to classifier setting, let's say it's a, if you think of a classifier, I would have an input X, f of X, and I would have, let's say there are a little number of actions, then I would have M classes, right? So this second one is very similar to that. In the first one, you could give, it would be equivalent to saying, oh, if I give a feature vector and the class label, tell me whether it's a good label or not. So maybe, produce 0.9 if it's a good label, and if it's a, bad label, produce, 0.1. You could do it that way. Okay. But we're going to put the second option. And
so Professor, in the first case, is it like we'll have to iterate over all the kind of actions and then say which is a good one.
Yes, exactly. So I mean, so there's not much. I mean, if your actions are not, typically actions would not have metadata. So if there would be just discrete choices, like very similar to classifiers, class A versus class B versus class C, then you don't really want to, do it this way where, because you'll just be passing a one-hot encoding or something like that, right? Because for the second argument. So you could just say, I'll just pass a state and I'll just produce for each class what's the probability that that's the right class. Okay. Instead of doing it this way, you can, even for classification, you could do it this way, right? So you can pass the feature vector and a one-hot encoded version of your class label and say, what's the, can you, your prediction should be, close to 1 if it's the right class, if the right coordinate of one hot encoded second argument is to the right class and so on, right?
Got it.
So yeah, so basically it's just one time. So yeah, here we'll do a for loop a few times. Yeah.
Okay.
Any other question at this point? So what we're trying to do is move away from a table representation to a function, and we'll get to the DQN version of it, which is a specific function that they use because they work with Atari games. And so for Atari games, you can imagine that the state is going to be screenshots of the game, and actions are going to be the joystick moves. Okay, and so there's a specific function approximator, a specific neural network that they'll use. Okay, that they used. That's where we're going towards. So yeah, if there are no questions, then let's move forward. So basically, this choice. So basically, the parameters are the same, and this choice just depends on which function class. So maybe it's a linear function class, and I just wrote it earlier, and I'm going to rewrite it again. You could have a adjusted decision tree. You could have a neural network, and this is what we're going to focus on today. Okay, but you can have many, whatever choices that you've seen in supervised learning. All of them are fair game here. Okay, so now, so before I get to, so what we need is, okay, we're going from a table to a function, right? A function to represent the Q state action value function. What we want to go towards is to somehow fix our previous Q learning algorithm, right? So Q learning algorithm, it was actually a tabular Q learning algorithm, so it really relied on a table. So we have to change that, right? So the update rule has to change to something else. And to do that, we're going to do it in 2 steps. First, let's just discuss approximation itself, function approximation itself, and then we'll change the update rule in Q learning. Okay. So what do I mean by try to understand, understand the approximation itself? So I mean the following, right? Let's say you do have access to the state action value function for a given policy. Okay, so this is a slightly different problem, a well specified problem where I have a policy. For that policy, I have computed state action value function for every state in action pair. Okay, so let's say I have that information. Somehow, like for example, how do I have that information? Maybe when I query for a state action pair, I can get back this number. Let's say I have this number. Okay. Now, so which means that for every state action pair, if I query, I'll get some number. But let's say now I want to approximate the state action value function using a parametric function with some parameter W. So I want to approximate the right hand side with some parametric function. Okay, that's what an approximation means, right? Now, how would you do that approximation? You would say, okay, I have some target values. Maybe for I have some target values that I can get for a bunch of state action value pairs. So let's say S, A. So maybe S1, A1. Use the lowercase letters here. Okay, let's say S1, A1, S2, A2. I have the value. Okay, so value would be the Q pi of S1, A1. Value 2, and so on. So if I have this data, okay, which would be this value would be the true value, then I can say, okay, I just need to figure out W such that this function approximates at those S1, A1, S2, A2 close enough to what the true value is. That's just a regression problem, right? I can just do a least squares regression problem, and depending on whether this function is linear or nonlinear, I'll get a more complicated regression problem or a simple regression problem, right? So that's how you would approximate. So I want you to think in terms of what's the effect of approximating if you knew the ground truth. So if you knew, if somebody tells you this is the true state action value function, but you want to approximate that function using some other function, then you would just write, okay, some criteria for how good the approximation is, and that's this criteria here, which is the expected difference between the truth and what you've approximated, square potentially, and this expectation is over the randomness. For example, you could have randomness over actions. You could also have randomness over states, so you can include that. So let's call this the score. So for every choice of W, approximating function. So every time I change W, I get a different approximating function, right? Every time I change W, I get a different approximating function, and for every W, I can give a score. So with that idea, so once I get this, for every W, I can get a score, because since I said we know this true thing, you can imagine how we can do a stochastic gradient descent. So for stochastic gradient descent, let's say we can drop this expectation. Okay, basically recall for stochastic gradient descent, you basically work with batches. So you can think of a batch size of 1 if you want. So if you drop that expectation, you basically have a squared function, and if you take the gradient with respect to the parameter, okay. So this is basically something like a minus x the whole square. So you can find the derivative with respect to x. So this would be minus 2, sorry, a minus x, right? Yeah. Yeah. So you would have something like that, right? So basically this, I would say, let's call it d. So dx by dx. Okay, that's just 1. But if you go back here, if I take the derivative of jw with respect to w, okay, then what do I get? So the difference is that now it's basically the equivalent to saying what is the derivative of something, some constant minus some function of x, the whole square. That would be equal to minus 2 a minus g of x times, right? And you can kind of drop this minus 2 in the sense that you can bring it to the left-hand side. So that's what we've done here. Minus 2 became minus 1/2. Okay. So the gradient of j, or the loss function, or the scoring function with respect to w, is just the thing inside the square, times the gradient of the second argument, or something like gradient of the second argument, which is what this is, right? Okay. So this is something that is just a recap for many of you. I'm just explicitly writing it. And so once you have this gradient with respect to the scoring function or the loss function, you can change the, you can do a gradient update, which would be just w new. Okay. Think of w as a vector if you want. It will be equal to w old minus alpha. Oh, okay. Here it's, yeah, because there's a negative sign already here. So okay, let me write just minus alpha. That's gradient of j of w with respect to w, something like this. And what is gradient of j? So basically the above equation is just the same as this, okay, where you substitute what j of w is, and because there's a minus sign there, you don't have a minus in front of alpha. Okay, so this is what you would do as a gradient update. Okay. So that's so far what I've said is all this makes sense when you have a ground truth, or if you have access to a state action value function. Okay. So let me further just give one concrete example of what the approximating function is, and we'll keep it simple. So let's look at a linear function approximation to just kind of eyeball what the update rule looks like. Eyeball what the update for the parameter looks like. Okay. Ultimately, we want to go back to Q-learning, but here we're just talking about, here's a function, here's another function which I want to approximate the first function with. How would I do that? Okay. So let's start with a linear function example. So let's say my state action is represented by state and actions is represented by a feature vector, by which I mean that think of it this way, right? So if I give you a state and an action, okay, if I give you a state, let's say state is some 10-dimensional vector, or a, let's say state is 10-dimensional vector. Let's say action is a label, or it could also be a 5-dimensional vector, right? Because actions can also be, oh, with this much add this much acceleration to the car, add this much braking to the car, turn the steering by this much angle, and so on. So there could be, action itself could also be a vector or a label. Okay. If it's a label, just think of it as one hard encoded vector. Then you can create a feature vector using those two, right? One simple trivial feature vector is just to have S and A, right? So this would be 15 cross 1, because I just said, S is 10 cross 1 and A is, let's say, 5 cross 1, for example. You can kind of drop the X part if you want. But, this is just, is a more general representation for a function, a feature vector, which depends on both state and action, okay? Now, if you have a feature vector like this, then you can have a function approximation. Here's an example of function approximator, which is q hat of s comma a comma with parameter w. It's just going to be this feature vector transpose a weight vector, okay? Which, if you really want to elaborate it out, it's just the sum of each component. Let's say this feature vector belongs to Rn, then it's just the sum of n products, basically. And if that's the case, then what's the gradient of your gradient of this function itself? Because we need the gradient of the function, because you saw for squared laws, we just need the gradient of the function in the update rule. So gradient of the function is the feature itself, because gradient of the function with respect to the parameter is the feature vector itself, okay? This is also in Rn. And the update rule, so W new is being updated to W old. Okay, so by the way, this is also belongs to Rn. So in the sense that the weight vector, in this case, the parameter vector, is also in n dimensions. And is updated using W old minus alpha. But we just saw that for squared loss function, when the second argument is the one which depends on W, then basically the minus is replaced. Although you're doing gradient descent, the minus is basically cancelled out. So basically you have plus alpha times the truth, let's call it truth, or the value that you want to approximate with, minus q hat at this given s comma a at the given parameter, W old actually here, times the x. Okay, so this is going to be x of s comma. So recall, this is n-dimensional, this is n-dimensional, this is a scalar, and this is n-dimensional. So that's the gradient update. So we just went through the gory details of like what does an update look like for just approximation. Okay, and now we're going to talk about how do we bring in approximation into the Q-learning idea. Okay, Q-learning algorithm that we saw for tabular setting. So any questions about just approximation itself before I get into okay, so this is, I assume this is a little bit straightforward. I mean, how you would do an update, just approximating one function with another. So now let's talk about like now bringing in the approximation to Q-learning. So let's recall what the Q-learning update is. Q-learning update is the new value, basically. Let's call it new, is old Q value plus alpha times the steady error, which also had this old. Okay, so this would be nothing but 1 minus alpha times the old value plus alpha times this new information. Okay, so new information, because you will get new information this and this once you play action AT at state ST. So this is a Q-learning update, and we'll somehow try to relate this to the squared loss expression that we had. Okay, so what we had missing previously is this, right? So what we are missing previously is this. So in the previous 3 slides, we said, oh, let's assume that we have a target Q function, and then we'll talk about how do we update W to approximate the target function well. But we don't have the Q's, Q pi, little Q pi. So we're gonna try to interpret, how to replace the q pi with something else. Okay, and you'll see that's quite intuitive in hindsight. So let me say that if you have this q learning update, then you can imagine that, let's say I keep updating this q value. So as you saw in q learning algorithm, you have a for loop. So at every, at t is equal to 1000, I'll do one update. At t is equal to, 100,000, I'll do another update, and so on. But at some point, your q values will kind of stabilize, right? So this, from the old value to the new value, there should not be any change. And that's what convergence means. And we wrote roughly a statement like informally what, that q star, qt will be equal to q star eventually, right? So after maybe t is equal to 10,000 or t is equal to 1,000, 100,000 or something. So this will not change, which means that if these two, this value and this value don't change, this value is equal to this value basically, then this should roughly be equal to 0, right? So TD error or TD0 error should be equal to 0. So, or basically at optimality, when we've kind of learned the best Q. So recall here, I'm not talking about approximation. So we will learn the best Q, but when we learn the best Q, basically the TD error in expectation should be 0. What is the expectation over? Is just the randomness, the ST and AT, which are potentially random. Sorry, just ST plus 1 as well. So as well as RT plus 1. So among the randomness, so don't worry so much of the expectation, but what I'm saying is that the TD error should be 0. So because we want this number to be close to 0 is kind of what signals that we have learned, we have learned the Q value. So from that, we can just hand wave and say, okay, if we want this error to be 0, the TD error to be 0, we want Q value to be very close to this target. Okay, so the Q of ST, AT to be very close to this target. So why don't we just use this guy as the reference? Okay, as the reference, here. Okay, so yeah, as the reference for this. Okay, so Q pi of S comma A. In the squared loss function that we said, okay, there we can just use the one inside the box. Okay, so intuitively what I'm saying is try to minimize the empirical error between this target and this. So both have W's, but we're gonna address that in the next few slides. But basically your target is going to be you're doing function approximation, so now you have this Q function. You're trying to learn W, so you're going to do a stochastic gradient update on W, but to learn W, you needed the reference function, so that the true ground truth. Instead of the true ground truth, we'll be using this. Okay, so we'll be using this as the reference ground truth. So as instead of the ground truth. Okay, so. Is that clear? So basically what I'm saying is you're going to do a minimization over W of basically R. So let me use the same notation. RT plus 1 plus gamma max over A. Q of ST plus 1 comma A. And this is going to be your reference. So, okay, maybe I should not close the bracket there. I mean, given that there's parameter W minus Q of ST and AT. And you do the whole square, and expectation with respect to S and A and all the randomness ST plus 1 and RT plus 1. Okay. And ST, AT, yeah. So this is what changed from the previous slides to this is just the reference change to something that we can get during the agent's interaction with the environment. Okay. Actually, I should also add W here. So this depends on W and this depends on W. So we want to minimize our W. So you can imagine it's not still the form of some sort of supervised learning problem because your targets also depend on W and your function that you approximate, it depends on W. That's fine. That's natural. But there is some issue with this, and we're gonna fix that pretty soon.
Uh,
Yeah.
so Professor, in this equation,
Yeah.
the component which is multiplied with gamma, the max of A.
Yeah.
So this is basically, intuitively it says, taking an action at st+1 would yield us the maximum reward over time, right? As in, it's the future that's being captured in this part. So
yes. So
and
this gamma times this is actually capturing the future. Exactly. This is not
yeah,
reinforced. There's not supervised learning. If you had the zero, basically you can
yeah,
think of that something like supervised learning. But this long-term aspect is being captured here.
okay.
Yeah.
But and we're also countering it with a minima. So isn't it getting
Oh
nullified?
no, this is just saying minimize the difference between.
Uh-huh.
So think of function approximation, right? You need to approximate the Q function with some target, but the target is I'm just saying that the target is this. Okay,
Okay.
so we're trying to change W, so
Okay.
W here, such that these two terms are close to each other. We're not trying to make the value functions of small or large.
Okay. Okay. Oh yeah,
Um,
get it. Get
this
it.
is just trying to learn the parameter of the Q function.
Okay.
But we certainly want, we always want to, so we want to learn. So let's say, let me write the original problem is to maximize, you know, let's say because we are only having parameter W, we want to maximize QSA of W. So if W characterizes all possible choices of Q function, then I want to pick that W which maximizes the Q.
Okay.
Okay.
Got it.
Because W means W leads to some policy. That
Hmm.
policy is what's the policy here?
Okay. Got it. Got it. Yeah.
Why, and you can say, oh, how does W lead to policy? Because given W, there's a Q. Given W, there's a Q of Q function parameterized by that W, and given that Q function, I know what the policy is. The policy is just max over A of Q of S comma A.
Okay.
Given the W at every S. Okay, so at every given state, what's my policy is, oh, I'll given W is fixed. You gave me W, therefore I know this function. If I know this function, I know for every state, for every, let's say, 5 actions, I know what the scores are. Take that action, which is let me just say
Okay.
argmax. Take the action which is maximizing that row. Basically, it's very similar to what we were talking about in tabular Q learning as well.
Right.
Right?
Okay. Got it.
So basically, W is characterizing a policy. This is the policy. Argmax over A for every situation that you're in, every state that you're in. What's the action to take?
Right. Okay. Got it. Yeah.
So the original problem is always this, okay, and that's what this problem is the same for Q value iteration. I mean, these are all algorithms. Q value iteration, Q learning, or Bellman optimality equation. These are all related, but the original optimization problem is just this: find the best policy that maximizes the total cumulative reward.
Okay.
Right? That is the issue. That's the goal of reinforcement learning.
Right. Got it. Yeah.
Okay, let's talk about. So what we've done so far is just talk about, oh, here's function approximation. Here's how you do generally function approximation, and then how is it related to in Q learning? What's the right function approximation uh, equation? Okay, so we will revisit this pretty soon again. I mean, in the sense that we'll see this equation again, so so that it reinforces our understanding. But now let's talk about DQN. Okay, so the first case study that we mentioned at the beginning of the class. So DQN, I think last time I showed some um, animations. Maybe I can show it again. Let's see. Atari. Okay. Okay, so Atari. So, I mean, so just to, before we get into DQN details, basically this is an example of a game. This is Breakout. Okay. So basically, so this is actually, in fact, from DeepMind, the researchers who did this. So they're showing how their agent performs as it learns more and more about the environment. And learning more about the environment is basically maintaining that queue, updating the W parameter. Okay. And we'll talk about what is the function approximation being done here. It's going to be just, in fact, it's going to be just a CNN. So you've seen CNN in lecture 2, so in lecture 3. So it's basically we're coming back to that. But essentially, um, uh, there's some function approximation. There's some update of W going on in every episode. So for example, an episode, there's going to be updating going on in a periodic manner. We're going to discuss what is that periodicity, and when is this update of W, this SGD type or this gradient update of W going to happen. We will discuss that. But as W is being updated, hopefully after later rounds or later instances of W, after some time, you have actually learned good W. A good W you've learned means basically that your policy of controlling the paddle at the bottom, you can actually get high rewards. Okay, so that's essentially what we will talk about. So the algorithm behind basically this game playing agent. Okay, so let me come back. So in your assignment, we're going to do the same, the algorithm that we're going to discuss right now, but we're going to use a different environment. Okay, so here we're going to talk about Atari learning environment or Atari games. In your assignment, it's going to be another simple environment called Cartpole. Some of you might have seen it. It's basically about balancing a pole vertically. Okay, so you move left and right, and if depending on where you move, it's going to fall. The pole is going to fall right. So if the pole is falling towards the right, you move appropriately so that it balances back. And so your reward is how long you can keep the pole vertically before it falls off. Okay, and so you learn a policy which can stabilize the pole, hopefully, in your assignment. So with that, let's come back to Atari. So here's a snapshot of about 50 games in this bucket of games. So in that context, we're going to talk about a specific algorithm, and that algorithm is going to fix some issues with naively doing function approximation. Okay, and we're going to discuss that and some details about, and we're going to discuss the detail of the algorithm. It's called DQN, and what it fixes with naively applying function approximation. Okay, so when you pick a function, so when you pick a function to approximate the state action value function, you could, you may typically have a nonlinear optimization problem, right? So the moment you pick a neural network and you have few hidden layers with some nonlinearities, you have a nonlinear optimization over W. And we have seen a lot of nonlinear optimization in many of your assignments. You have been doing nonlinear optimization when you talk about sequence models or training CNNs, whatever it is, right? And the moment you have nonlinear optimization, a lot of things can go wrong. Okay. Which is related to basically, and things are basically that, or things that can go wrong in RL is going to be that you will diverge. So W is going to keep exploding, and you're getting bad and bad policies basically, or you may be, oscillations just mean that you're circling between some parameter values, or you're basically doing worse in terms of like actions. Okay, so you're basically not getting to the right policy. Okay, and that's somewhat specific to I guess RL. The issues that come up in RL are slightly different from I would say are in addition to the issues that you'll see in supervised learning. In supervised learning, also gradients cannot explode. Gradients, you may have dead ReLUs or dead neurons, things like that. There's all sorts of issues with nonlinearity, but there's some additional issues with RL, which is that the data is not IID, right? So if let's think of the incremental setting. So in incremental setting, I took, I'm in state ST, I took an action AT, I got a reward RT plus 1, and I went to next state ST plus 1, right? And then let's say I was doing incremental, as in like very similar to the what Q-learning algorithm we saw. Then the next step of the for loop, I'll be having ST plus 1. I may take some action AT plus 1 and RT plus 2 and ST plus 2, right? This is the same as this. right? So there is dependence. So if I do a weight update, maybe weight update some W old to W new, so the W older. So maybe from I got this new data, this data, I went from W older to W old, and I got this new data, this next new data, I went from W old to W new. You can see that there's dependence across observations, right? This dependence is not there in supervised learning. You can permute your observations, it doesn't matter. Okay? And so that leads to weird things like, the W's, in addition to what you would see in supervised learning, supervised learning based training. Things will oscillate. Policies may be pretty bad and so on. Okay. There's also that max operation, right? So there's a max over action. So if you change W slightly, maybe you switch from action 1 to action, let's say 10, and action 10 is completely different than action 1. So for example, action 1 could be move forward in the maze, and action 10 could be move backward in the maze. So there's a lot of sensitivity to your data trajectory, right? So if you move forward, then there's a certain state you visit, and move backward, it's a completely like a different state that you will visit, and therefore the next observations will be completely different, right? So basically, these additional issues typically crop up when you directly use function approximation in a somewhat naive or straightforward way. And DQN is basically tries to fix those issues and in some specific ways, and we're going to look at that. Okay, so it's this whole thing is just a case study. This is not the only way to bring in function approximation and into RL. There are many other techniques, but for us, since we saw Q-learning and we learned a little bit about function approximation, DQN is a good example algorithm to know about. Okay. And we'll in fact look at a batch optimization technique. And so in tabular Q learning, everything was incremental. So in a given state, it took an action, just update the Q value for that, right? You can do the same incremental thing with the weights as well. If you're in a state, if you took an action, you get that 4 tuple. Given the 4 tuple, just update the W using the SGD equation, right? You could do that, but DQN will choose a batched approach. Okay. So any questions up to this point, like where we are heading towards? We are basically going into the details of the specific algorithm, okay, which is used to, which we'll talk about it in the context of the games, the Atari games.
Could you repeat the second point? Like, policy or value may be too sensitive to action.
Oh yeah. All I meant is that all I meant is that your target, recall, if you go back here, I think all I'm saying is this target. So if I change W slightly, maybe, instead of action 1 was the maximizer, instead of action 1, action 10 is the maximizer. Let's say action 1 is go straight forward and, go straight, or let's think of the breakout game. Maybe action 1 is to go to the left, and action 10 is to go to the right. Then basically a slight perturbation W is changing your Q value slightly, and therefore your next sample is different, right? So slight change W is just making the so it's not about I would say you change the action, and then subsequent actions will be very different, I would say. Okay. So actually that's I guess a very informal point. I didn't think it just means that the objective function is too sensitive to, because of the max operation.
Okay.
Changing the future trajectory quite a bit. Okay. I mean, the future trajectory, there's dependency. Basically, I think, I guess first 2 points, these 2 points are related. Both are about this dependency on observations across time.
Okay, got it.
So let's now talk about DQN for Atari games. So So what we'll do is do a very quick recap of CNNs for 2 minutes. And actually, this is pretty much the last lecture on RL. So next lecture, we're going to look at text models like transformers and attention and so on again. And the lecture after that, we're going to look at vision, which includes CNNs and so on again. But for now, for the description of DQN, we'll quickly recap as CNN architecture. Okay, so so the term, I haven't referenced the term deep reinforcement learning yet. So now we are in the stage where we say, okay, we are talking about deep reinforcement learning because our function approximators are going to be deep neural networks, and we're gonna learn from simulators or environment to take optimal actions eventually. Okay, so we look at DQN. It's from 2013, and AlphaGo. In fact, we'll look at the AlphaGo. I guess AlphaGo Lee. Uh, just the because now there are many variations of AlphaGo 0, and Alpha 0, and so on. So what we're going to discuss is the one of the first versions which actually beat the Go player back in 2016. Okay, so those are the two agents we'll see. And you'll see that so these are just two, from a highlight perspective, these are just two specific algorithms or schemes to do well in their respective environments, right? So that's the takeaway. So these are essentially just case studies. There are many algorithms beyond these, and they've also been improved quite a bit. And you'll see that the moment you get into the details of DQN and AlphaGo 0, there's some additional points that they try to take into account according to the domain and so on. And that's where I think that's something that I'll highlight. That's what you will take away with that. There's if depending on the problem, you may have to go from the general version to a specific algorithm which may exploit something in the problem. Anyway, so let's come back to deep learning. So this is an image that we saw, or at least we discussed a long time ago. Basically, this jump from say 2011 to, let's say, 2014-15, where you went from 70% absolute accuracy to plus 20% improvement in plus 20% absolute increase in accuracy. This is top 5 accuracy, by the way. So this delta was kind of caused by models which are not hand engineered, or models which which kind of exploit the properties of images in a nice way. So for previously, for example, you would have an image, you would create a lot of features. So this is just histogram of oriented gradients and things like that, or edge detectors and so on. They're all feature engineering that handcrafted feature engineering. And then you would just apply a shallow model like an SVM, okay, to do, let's say, image classification. Instead of that, you would have the raw image as input, and you'd have a lot of con layers and fully connected layers, and eventually you would just have a classifier. And that's for example, the ResNet 18 or ResNet 50 or whatever you worked with in assignments example is an example like this. Okay, it's not, the architecture is not this, right? ResNet has residual connections and so on. But yeah, so that's what's happened since 2013 onwards. Okay, and we know why why CNNs are good choices for images. They have they really do weight sharing in comparison to, let's say, fully connected layers, and they also take into account translation invariance. Not just pooling anyway, it reduces the number of weights as you move forward in the architecture, but you also have translation invariance because you're using filters which slide across the input tensor, for example, at any given layer, right? So there is some like the later layers will see larger parts of the input, whereas early layers will see small parts of the input, okay? And then they slide across input tensors. So anyway, so CNNs are well aligned with the properties of images we expect to have, like the translation invariance and things like that. And so they work really well. And the idea in DQN is to exploit or to use use them as function approximators with screens themselves as being inputs, okay, as images. So overall, the environment looks like this, right? So there's a screen from which we're going to make an observation, and this brain here represents our algorithm, so DQN, okay? And the algorithm is going to produce an action, AT, and the action is basically some move on the joystick, and that's fed to your simulator here, in this case the console, and then from the simulator you'll actually get you'll basically be seeing the screen. At the top of the screen you get to see the reward signal, and that can be processed for example using OCR or something if you want to get the reward, instantaneous reward. Okay, so That's the environment. Now let's get into what the function approximator looks like. That's, as I said, is a CNN. So we use a CNN as a function approximator. But there's going to be two key things, and that's what I wanted to quickly discuss. First is there's going to be a batching, so batch optimization, so a batch version of these weight updates. So batch, I just mean that, if you look at the tabular Q learning, there was a update rule, right? So the update rule, you would call that update rule incremental, and so in contrast to that, here the update rule is like a batch rule. Okay, so we're going to use a batch of these 4 tuples: state, action, next state, reward, to update W or weights. Okay, and there's another thing. So how do you maintain a batch and so on? How do you get a batch and so on? We'll discuss that. And the second thing is we're going to use an idea which is to freeze the targets. So if you recall, there was this R plus gamma max of Q, and there was a dependency on W. And then there was also minus Q. There was a dependency on W. Okay, so something like this, the whole square. You had an objective with targets also depending on W, and your function that you optimize for, of course, depends on W naturally. So we're going to freeze this target by not changing this W, as if this is a fixed constant. We're going to do that, and we'll see how we'll do that. Okay. So those are the two changes in the algorithm, changes that will help us go from, applying function approximation in a very straightforward manner to a version which really works and plays these games really well and beats human players. Okay, and this was really not possible before. I would say this was only possible this last decade. Definitely not before, let's say, 2010 or 2011. I mean, it was possible. I wouldn't say it's a huge delta, but it was not as surprising as it was with the DQN method. Okay, so the method was itself there much before. But to apply to Atari and actually show and demonstrate that it actually works really well is new in 2012, 2013. So let's look at the function approximator. So it's actually the input is a stack of 4 previous screens, okay, screenshots. Here they're saying is as frames. So the screens are 84 cross 84. Think of grayscale images. So 84 cross 84 scale sized images, and 4 of them. Okay, so they just look at 4 snaps or 4 frames. Okay, and just concatenate them together. And so that's my input. And then they have 16 8 cross 8 filters, followed by 32 4 cross 4 filters, and then 2 fully connected layers, which is the 256 hidden units in one fully connected layer. And I think, okay, I think it's basically one fully connected layer, and the output layer has 18 outputs. Okay, so that's pretty much it. It's actually not a deep network, right? It just has 2 common layers and one fully connected layer. But that's the architecture that was used back in 2012. Okay. And this reference is actually a Nature paper from 2015. And so if you're interested, you can look at the paper. Okay. So basically, this network here is trying to represent, so this here is the state. And this output here is the Q, is supposed to at least approximate Q of S comma A, A1 all the way to Q of S comma A18. Okay, so it's 18 dimensional, 18 numbers. Then given these 18 numbers, you know what action to take. You just take the max over whichever coordinate is the highest. Maybe that action is the most, most likely or good one. And so you take that one as your policy. Okay. So, and you don't have to, so you can also do exploration, and then the reward is basically the delta, the change in the score for that action that you took. Okay. Like for example, if you recall, go back to breakout, if you move the paddle left or right, and the ball is nowhere close to you, then whether you move the paddle left or right doesn't matter, right? So, so for example, there the reward would be 0. But if the ball is, you move the ball left and it actually saved the ball and it bounced back and eventually hit, after several time steps, then after several time steps, you'll see the reward. Okay, so for the immediate reward would be 0. So that aspect is also there here. Okay, so let's now talk about the 2 specific extensions or modifications necessary to be able to get in practice the good performance for function approximation of Q network of the Q function. So the two things, as I said earlier, was something to do with badges. Okay, and that use the underlying idea there is called the use of experience replay. Okay, and the second idea is called fixing Q targets, and I briefly mentioned it earlier, but I'm going to revisit that again. So what is the idea here? The idea is to take actions according to epsilon greedy policy, just like Q learning. So this is the same as before that we have seen before. Now we just have to figure out how to do an update, right? So an update in the traveler Q learning would be an update of an entry, a cell of a matrix. But here we need to update the weights. Okay, so we're going to update the weights, but to do so, every time step, what we can do is store a 4 tuple in a memory. Okay, so memory, just think of it as a database if you want, or a list or something like that. So basically, we'll store every 4 tuple as a row or an entry in a database, a record in a database, and then to do the update, we're going to sample a mini batch. So we're going to sample a mini batch of these 4 tuples from the database. Okay, so you have these 4 objects, or if you know, like state could be vector and next state could be vector, but let's say action and reward are scalars if you want. And so you'll get these 4, 4 entities in this 4 tuple. You'll sample many, a few of them. Okay, and you'll use them along with the following modification. You'll also freeze the parameters in the targets to some previously learned old value. So remember, we are updating W's, right? So when we're updating W's, we know, let's say we keep track of what was W at the 100th update and what was W at the 200th update and so on. So we can just remember, if we can remember that, then we'll fix the parameters in the Q learning target. Remember the squared loss function to be maybe the most recent 100. Let's say we are in the time step T is 751. We are in the 751st time step. Little t is equal to 751. Then maybe W minus is kept the same as whatever it was at T is equal to 700. Okay, maybe every 100 steps we change it. Okay, so given those two, given sample the mini batch and free frozen the target, we're going to do this minimization, okay, which is written here. So it's the same as before. So W subscript I just represents the ith update. Okay, so yeah, the ith update. So we're gonna try to minimize this over Wi. Okay, so let's say we are doing the ith update. So we're gonna minimize this. So right hand side is fine. Sorry, this term is fine. The target term, as I said, we're gonna freeze it to some previous value. Okay, so therefore this is not a function of W, it's just a constant, right? If you wanted to change Wi, this term, the only place where Wi appears is here. So it looks like supervised learning. In fact, it is essentially supervised learning because we're also taking a mini batch. Once we take the mini batch of 4 tuples, state, action, reward, and next state, when you sample that mini batch from this replay memory, you may not necessarily get consecutive, consecutive last 10 such tuples, right? You may get, let's say the memory is of size, I'm going to maintain, let's say 10,000 such tuples. And when you sample it, when you sample some of these 4 tuples from there, this guys from there, you may not get a sequence of 10 successive ones, right? You may get, numbers from, these tuples from various different time points in the past. Okay, so that somehow gets kind of approximates this IID nature which is needed to get rid of this oscillation. Okay, and then once you have this loss function, you can just use a gradient step to update the weights.
Oh,
yeah.
So Professor, here, so for every mini batch, we're getting new W's. Is it that way?
Yeah. So every time we want to update, we get a mini batch from our replay buffer.
And does the replay buffer kind of gets refreshed? Is it like we have?
Yes. So let me explain that again. So what I wrote is bullet points over there. Let me explain with the diagram here. So think of the replay memory as storing at the 10,000 most recent 4 tuples. Okay, so the state, action, next state, and reward, right? So sorry, state, action, reward, and next state. Okay, they're getting stored every time step. Okay, we'll remember only the most recent 10,000 of them. Now, so we're getting this, and then we are taking, so the queue network is our policy, we're going to base our policy based on the queue network, right? So we're going to take an argmax at any given state that we'll read the state from the environment, and looking at the state, we can take an argmax over actions of, in that state, whatever our queue function is going to say. We're going to get those 4 numbers, right? If we pass it through our function approximator, out of the 4 numbers, take the one which is the highest. And we'll also add, some exploration. That exploration is not captured here, but with some probability, we'll take a random action. Okay. So this part we have seen, this part we have seen before, and this is just storing. Okay. Now this whole thing is about how are you going to optimize, and this optimization can happen every time step if you want, or the frequency of this optimization is not is not really related to us collecting data. Okay, so let's say we do this optimization every round, then so every time step, then what we have to do is from replay memory sample a mini batch. Okay, so that is the ith mini batch here. Sample a mini batch just means you get a S, A, R, and S prime numbers. Maybe let's say mini batch is of size 10, then you'll get 10 such tuples. Okay. Now what are we going to do? We need to update the queue network's W. So, or here I'm using theta for some reason. Basically, we need to update the W of the queue network. So we'll use the next state and R to get, recall this is the one with the W minus, which is a previously fixed W's. Okay, we're going to periodically update it. Recall our update frequency for the W minus was every 100th time step, if you want. Okay. So given S prime and R, we can compute this, right? Because we know S prime, we know R, we have the Q at the previous W. All we need to do is max over A, and then we can compute this whole number. Okay. That computed number is the target, basically, right? And at S comma A, we have we can pass it through the current parameter, and we get the Q at the current theta, right? So target minus this, the whole square, is what you're trying to minimize, and that gradient update will change from theta to theta nu. Okay.
Yeah, it's clear.
Yeah. Okay. Any questions by anybody else who's confused here? I mean, the block diagram should be clear. If the equations are a little bit confusing, you can go back and you can certainly ask me offline and so on, or you can ask me now. Okay, so this is essentially the DQN architecture. So it's basically using function approximation, but there's this additional thing of a target queue network and the replay memory. These two. Yeah, this is the first thing, and there's the second thing, just to take care of this oscillation and not converging business. And they saw really good results. Okay, and so that's the and the results are as follows, right? So the algorithm does not know the rules of the game, so it's not like chess or Go that we're going to talk about today. We don't know the rules of the game. In fact, we don't we don't do any feature engineering. So snapshots of this game screen are the input. Like I think we also saw a Flappy Bird example last time, right? So we don't do any feature engineering or even change the hyperparameters. What are the hyperparameters like epsilon, the epsilon exploration, or even the alpha, the learning rate for the this update of the weights, right, of the neural network. So you don't change anything, but so you keep them fixed a priori, and then keep using the same agent across all the agents, across all the environments, because all environments have the same screen, right? Of course, the games are different, but they kind of, you essentially use the same joystick with the 18 odd moves that you can do. So you start from scratch. You don't know anything about the game. You use the same network, with some random initialization and same fixed hyperparameters, and see how will they perform. And here you can see that for a large chunk of games, I mean, so this graph is trying to fit in a lot of information, but all it's trying to show is the performance over of DQN with respect to some other simpler technique, which is the, here it's, the gray thing is the linear function approximation. So you can see that there are some games where the linear function approximation is already pretty well compared to humans. So this is better than humans. This is worse than humans. So you can see that there are games where you don't have to use deep learning. You can really use linear function approximation and do pretty well, right? So here, for example, these games. But the blue bar, the blue bar is showing that the DQN agent is able to do pretty well, right? So DQN agent is able to do much better than humans in a lot of games. And there are certain games in the Atari, this collection of games where it doesn't do well at all. In fact, there's some game where it doesn't even get any performance. It's called Montezuma's Revenge, and then a lot of papers followed up papers came about and why this is not working and fixes for that. Okay, so so that's the performance of DQN. And instead of looking at that graph, let's look at a specific way to quantify how did these two additional extensions. So you can certainly use function approximation, but this target, freezing of the Q network, the target, of the target network, and this experience replay or the replay buffer, how did they help, right? So let's to study that, you can look at a simple what is called an ablation study. It just means that, oh, did me adding this experience replay or this replay buffer help? Did me doing this target freezing or not help or not? Did it help? Okay, so you can start with the most vanilla version. So you have no experience replay, and you just do Q learning, and these are the scores you can get. Okay, so these are the numbers that you can get for 5 games. Okay, so it's a subset of games from the Atari learning environment from the previous figure. And now let's say you started, you can do target, you can freeze the target, but there is no replay buffer. Okay, you just added one feature, but not the other one. Then you see some improvements, right? So you can see some improvements here. Similarly, if you just, you don't do freezing of the target, but you do introduce replay buffer, you already get, you also get a huge bump, okay, improvements. Not from, like, you can compare this with this and this with this. Now, if you compare with both replay and target freezing, then you see kind of the best results. Okay, and that's what they have reported in their paper. So that's an example. And you may ask, okay, this seems like a small network. How long does it take to, you can see that this is like literally two con layers and one fully connected layer. So it should not take much time. But actually, when they did it back in 2012 and 2013, each game took about 14 days to train. Okay, so each bar here, and they might have trained multiple times for each game to get here, but each game took about to learn a good Q network. Okay, so the weights, eventually should should reach to a good Q network, and therefore the policy which using that Q network should be good, right? So each game took about 14 days. So so back then, about 5 years ago, for example, Google came about try to build a infrastructure, basically try to parallelize some of the things so that they can reduce the compute from 14 days to 6 hours. Okay. Now you can on a single GPU machine, you can probably do it in a half a day or something, about 12 hours maybe. And everything fits in a single GPU memory because the network itself is quite small, right? So I will not discuss the details of what's the parallelization going on. It's basically multiple game playing, multiple simulators, basically, and from multiple simulators you're collecting data, this state action, next state reward, and somehow you're able to also propagate the the policy across these multiple um, multiple environments that you're playing. So it's basically parallelization going on here. Okay, so any questions about DQN? So there was only basically function approximation and then target freezing and replay buffer or replay memory.
So the 100 actors there are the humans who are playing, right?
No, actors just mean so here actors just mean it's a word from so there's some, so just like we are looking at value function based learning algorithms, there are some algorithms called actor critic algorithms which use both a value function learning, which both learn a value function as well as a policy function. Okay, so actors just mean you can just think of it as the agent, the RL agent acting in an environment. So 100 environments, basically.
Okay.
It's not humans here.
Okay.
So actor, you can see actor just means Q network interacting with the environment here.
Yeah. Right. Okay. Okay. Yeah.
Okay, so let's take a break actually. So let's resume at 5:16. Yeah. If there are questions, leave it, you can use the chat in the meantime. Okay, so welcome back. So there's a question here before we get into AlphaGo case study. So is using RL the ideal way to implement a CPU-based opponent player in single-player video games? Okay. If you want to design an opponent, that's a different problem, I think. So if you're thinking of like a two-player game in a game like oh no, wait a second. So the question is about so RL is a good way to design an automated agent who is the single player in a single player game. So if you want to model opponents, then that's a different issue, right? If the opponents are part of the environment, then you have to design the environment appropriately, and the environment could have its own AI to to make the opponents like for example uh, you know opponents that you have to fight with in different stages. The underlying technology behind them is not RL. Okay. Um, so the difficulty level changes the AI strength of the opponents, for example, in a single player game, but those opponents are not trained using RL. I mean, you don't have a control on them. The RL is about, so what we're seeing here is about, how a computer can play a video game, okay, by trying out different things, just like humans would do and do better than humans. Okay? And game is just a beachhead, I would say, environment. The whole point is that this can be used in more real world settings like recommendation systems or self-driving and so on. So I hope that answers.
Professor, one doubt regarding the DQN thing. So there you mentioned the Q target network. So it's just that we're computing using the old value.
Okay, let me just mute something. Well, just give me 1 second. Somebody start. Actually, everybody's muted now. Okay, so go ahead.
Yeah, so in the DQN architecture, we see the component, the Q target network. So it's not a network. I mean, there's no training happening there, right? It's just computing.
It is a network. So in the sense that, okay, let me, okay, I don't want to go so up. So let me just say, so there is this, okay, so let me explain that. So just to get the notation correctly here. So R plus gamma max. So let's say there's a state, action, reward, and next state tuple. Then max of a q of, let's say, S prime, and then max over a here at W minus, right? So this would be your target, and you would just try to minimize with Q, S, and sorry, let's call it A prime, A at W. So the square, square of this is what you would try to minimize, right?
Right.
Min over W. Now, this is actually a neural network as well, right? Just think of this as a copy of this network at some previous time, some previous time step. Okay, so if you just think of, let's say if you're using PyTorch, right? So you had an NN module based class extension. You created a class and you instantiated that object, right? Let's say a CNN. Just think of this guy is also an instantiation or is an object from that same class. Okay, it's just that you need to like export the state dictionary or whatever the values of the parameters from there to and keep them. You need to just remember them at snapshots. Let's say every 100th episode or something.
Okay.
Yeah, it is a network. You're not training them. Yeah, you're just reading the weights from some previously trained network.
Okay, so the W remains the same. I mean, it is not. I mean, we don't
W
train
minus, yeah, it's a different W. It remains the same for a bunch of rounds, okay, bunch of updates. Let's say 100 updates. And as the next update, you change it to something that you remember. So it's like a trailing, it's like a trailing, trailing values. Okay.
Yeah.
Trailing fixed values, I would say. Yeah, something that you had, something that you remember
Right.
from before.
But the backprop part happens in the other network. That's the queue.
Yeah, because this is the only, this is the only function now. This is the only thing that is dependent on W, right? Nothing else is dependent on W. So this is W minus. You just think of that as some other, instead of W, you want to use something else, you can use it. Let's call it V. It has different parameters. It's not changing. Yeah. Just this is basically, once this is fixed, this whole thing that I'm, upperlining is just a regression target. Okay. So that's some fixed number.
Right.
Okay. So it's a bunch of numbers, a bunch of inputs features. You just need to change the W so that those are close to each other. It's just supervised learning, basically.
Right. Okay. It's clear. Okay.
Yeah. Okay. So let's talk about AlphaGo. Okay. So what's going to be different for AlphaGo is the core rendering idea is going to be MCTS. And if I get to we're going to talk about MCTS first, and then if we have time, we'll discuss about what's the interesting thing that they did in AlphaGo itself. If you don't have time, I'm going to show you the paper, and you can look at it towards the end. Okay. But it's a very easy to read paper, so certainly we can look at it. So okay, so let's talk about AlphaGo. Let's stop this. So we're going to talk about the version from 2016. It's a little bit more actually more complicated than the subsequent versions. But at the same time, since that's the version that beat the #1 player at that time, so it's a good case study to look at the underlying algorithm, in this case, Monte Carlo tree search, and the use of deep learning there. Okay. So, and it appeared, the paper appeared, I don't know when when the paper appeared. Okay, it appeared in 2016. That's it. Let's talk about Go first. So it's just like so. I don't know if any of you have played this game before. Maybe some of you have played. It's a game. So if somebody has played, then I apologize for not explaining it properly. But there's a game very similar to chess. It's basically, I mean, different people have different estimations of how old this game is and how many states it has. But you can estimate the states. For example, the board is 19 cross 19 in size, the professional board. And at every location, you can either have a black pawn or a black stone or a red stone, black stone or a white stone, or no stone there. So you can imagine the number of states here. Upper bound, you can get a loose upper bound, for example. But basically, it has a lot of states. Okay, it's a few orders of magnitude higher than the number of states in the game of chess, for example. Okay, so what that means is that, let's say, so there's nothing stochastic here, right? So if I place a stone somewhere, and let's say I know everything about the opponent, so I know what the opponent is going to do, and then I can place a stone somewhere else, and so on, and we keep going, and the game ends when you have occupied the most territory, and there is no further moves to be made. Okay. So if you have occupied a lot of territory, in this case, for example, the white wins, and this is not the only way to occupy territory. You basically surround yourself, like you can have a bunch of white stones, and then everything inside is your territory. Okay. So the player with the most territory wins, basically. But let's say you place the stones and you know exactly what the opponent does. Still, it's very hard for the computers to really evaluate what's the best move to make. Okay, so there's no stochasticity. You know everything about your opponent. Rules are known. Still, it's very hard to figure out what's the best move to make. Okay, and it's very similar to chess in that respect. So here's a quick snapshot of what the state of the art was back in 2016. Back in 2016, These 2 points are slightly different. So back in 2016, Go was one of the only classic games, classic board games, which did not have, where AI agents were not beating humans. Okay. So when we say classic board games, think of checkers, chess, Othello, Scrabble, and so on. No, maybe not this one. So so in the collection of classic board games, Go was really still unsolved at that point of time. And the bottom figure here is just showing, here onwards is just showing what were the state-of-the-art RL programs, okay, programs based on reinforcement learning, and what was their level of play. Okay, for example, we know in chess, it's not, we have really strong chess playing agents or chess playing software which really beat humans all the time, right? But RL based program, in this case, I guess these are the names, were at this level, for example. But so just giving a sense of where RL itself could get you. Okay. But we're going to focus on Go, because in Go, forget about RL, no computer agent at that point of time could beat the best human player. Okay. So this problem is actually a specific instance of a search problem or a planning problem. And it's in particular, it's called the forward search problem. So let's recall, sequential decision making. We said there are 2 types. So it's called sequential decision making. There is RL and there is planning. Okay. So in planning, you know everything about you know the model. Okay. You know everything about the environment. You just have to figure out, so in both cases, you have to figure out PI, which is the policy, right? Going from states to actions. But in the planning side of things, in a planning problem, you know everything about the environment. Okay. So a search problem would also be an example here. Okay. So an example would be a search problem. Okay. And a specific variant of a problem in the planning side is called forward search problem. And this distinction is just, I'm going to explain it pretty soon. So this is the lay of the land. Okay, so we've looked at RL and AlphaGo. We're going to focus on planning and planning-based problems, in particular search and particular forward search. And inside forward search, we're going to look at an algorithm called MCTS. Okay, Monte Carlo tree search. Okay, and it's also going to use a deep learning. Just like in RL, we looked at DQN. So we looked at, in RL, we know what the problem is, right? So it's just maximize the total cumulative rewards. And here's an algorithm which also used deep learning. So these 2 are at the same level, this guy and this guy. Now, what is forward search problem? Forward search problem is just the following problem. It's basically a problem where you want to figure out what is the best action to take next. Okay, so it's a problem where you are in some situation, typically in some state, and you want to say, in this state, what's the best action to take? That's the only question you're answering. You're not answering what is the best policy. Recall, in general, in planning and RL, you want to figure out a policy, which is the full function. In every state, what should I do, right? But here in forward search, I'm asking, in this given state, what should I do? You don't have to tell me in some other states what I should do or what I should not do. Okay, so the problem is smaller, right? In this state, just tell me what's the best thing I should do. That's the objective here. And it's useful in the case when you cannot plan everything in advance. For example, in chess or even in Go, and you'll see even the state-of-the-art agents today, they will not plan everything in advance, in the sense that they will not say in every board state what's the best thing to do. You cannot, even to store that would be difficult given the number of states, right? But what they do, what these algorithms do, is in the given board position, what is the best move to make? That they can compute using appropriate algorithms, and MCTS is one we'll see. So let's go back to Go. So in Go, we want to say how good is the position S. Okay, so S is like the state, and you want to say how good is the position S, and what is the action that I should take in position S, right? So that what we can talk about state value functions and state action value functions. So for this slide, I'm just talking about state value functions. So let's say we want to figure out how good is the position. And let's say the reward function is as follows. So reward is 0 for everything. You won't get a reward at all till the game ends. And the game ends if the person the black stones wins, then reward is 1. And if the person white stone wins, reward is 0. Okay. So we are basically this first player. And a policy is basically both the policies of the player and the policy of the opponent. Okay, the white player as well as the black player, right? Um, and the value function, which is basically how good the position is basically the expectation over the policy of this terminal reward. Okay, starting from a state S. So value of a state S, which is this definition and the definitions of value functions we saw earlier is exactly the same, except here there's no summation because we are not getting any reward in between, right? So there's only the final reward when the thing terminates, when the game terminates, and the termination itself is not also predetermined. It can terminate in 100 moves, or it could terminate in 1,000 moves. Okay, it's just the probability of black wins given from the starting state. Okay, and what is the best value function? It's the best value function is what is the what is the best value function is basically the best you can do as the let's say the player with the black stones, given that the white player will do their best to minimize your value, right, of this value function. Okay, so recall pi is just this tuple of your moves, your policy, and the opponent's policy. What is the best thing you can do for the worst thing that the opponent is going to do in terms of value? Okay, so that's the best. That's the optimal value function, and then the corresponding policy is what is the optimal policy that the player with the black stones has to play. Okay. Any questions about the setting up of what the reward is and what the policy is? Okay.
Here, it's completely the state value function, right?
Yeah. For now, yeah. Here I just said, yeah, this is the state value function. Good point. I just mentioned it earlier, but we can talk about state action value functions as well. Okay. This is just to give. I mean, this is just a formalism. So for what is the rewards and what is the value of a state? Yeah. I mean, so although I introduced value of the states here, they'll come back later. Okay, much later, and we'll see. They're not the central ingredient at the moment.
Okay. Yeah. Isn't it like for panning problems, the state value function is more dominant than the action value function?
No, they're related, right? I think we emphasized it last time. So V of S is nothing but sum over. Oh, sorry. You don't even do sum. V of S, if let's say it's the deterministic policy, then it's just a max over A of Q of S comma A.
Oh, yeah.
This is a relation.
Right.
So it's not like one is better than the other. They're just related to each other.
Okay. Oh, yeah.
Okay. So so that's the game of Go. But let's come back to the forward search problem. As I said, in the current state, which is the current board situation, what is the action that you take, right? So the forward just means that we're going to do a look at, we're going to do a look ahead in the sense that, so let's say you're playing the game with an opponent, and they say you're in a certain board situation and you want to make a move. Okay. Now in forward search using simulations or any, in forward search in general, what we're going to do is we're going back to our drawing board and say, oh, I'm in the situation. Let me kind of simulate what all can happen in the future. Okay. If I simulate what all can happen in the future in my imagination, or, it's not on the original board where I'm supposed to play, but I think of a copy of that board where I can now imagine, okay, if I do this person's going to do that, and then I do this, and this person will do that. So these are all the trajectories, let's say, that can happen. Okay. So I can do this, then the person is going to do that. I can do something else, the person is going to do that, and I win, let's say. Right. So given all these trajectories, that would be my, I can look at all these potential paths that can happen. That's essentially a search tree. Okay. That's a tree of all the things that can happen from now onwards. And with the current state as the root. And then you can kind of summarize, okay, if I take the, maybe my initial move is like move 1. or maybe move 2. Maybe, if I take move 1, there's a lot of chances of me ending up in good states. Sorry, those are not just the good states, but there are a lot of chances of me ending up in good states. And maybe if I take action 2, maybe there are only a few chances where I end up good states. Maybe I should take action 1. So that's the idea. Okay. And the model just means that, in Go, there's really, or Go or any board game, there's not much rules. I mean, the rules are pretty simple. The state transitions are pretty simple, but you can imagine the same thing where you have to access a simulator to tell you what the next state is going to be once you take an action, right? Yeah. So that's what a model of the MDP means. Yeah. So basically, the idea is you don't solve the whole environment, solve for the policy for the whole environment. You just solve for the sub MDP, or just that current starting state ST. What's the best action to take? Okay, that's the forward search. And we're going to use simulations in the sense that given the search tree, we'll not be given the search tree. We're going to be just given the state and and ask the question, what's the best thing to do? But we are given, a model of the MDP. And so we can construct the search tree itself, if we have a lot of time, or we can construct something that approximates the search tree, and therefore we can answer whether action 1 is better than action 2, for example. Okay. And in particular, we're gonna do the following, right? So we're gonna simulate episodes of experience. So simulate episodes of experience from now, which just means I'm in state ST. So this is all under my imagination. So I have to play the actual at ST. I need to play an actual let's say move with respect to my opponent. But I'm going to just copy that board, and just in my mind, or basically on, if I have access to a computer, I can simulate what all can happen in the future, right? So that I'm going to do using, by not looking at the whole search tree, because the whole branching of all the things that can happen from this point onwards is too much, right? And we saw the number of states being too many. So I'm just going to sample a sequence of things, let's say one experience that can happen, which just means that I'll play some action, the opponent plays some other action, I play some action, the opponent plays some other action, and so on. Okay. Given that it terminated and maybe I won or lost, that information will be helpful in me figuring out whether action, the action that I took at the beginning, the first action that I took is useful or not. Okay. When I say apply model free RL, it just means that I'm gonna I'm not gonna think about, the model itself. I'm gonna think about either, in particular, I'm gonna think about actually Q state action value functions, okay, which are, the moment you're maintaining state action value functions, it's basically a model free, I guess, scheme, because you're not explicitly maintaining any model of your environment, okay. In contrast to, there are other techniques we have not seen in the past 2 lectures, but there are other techniques which explicitly construct a model of the environment and then solve for the policy. Okay, so we have not seen that, but just think of it as we are just going to maintain state action value functions somehow. Okay, to figure out what's the best action is. Recall that that's our objective. So simulate. So okay, given the same starting state, let's just get a bunch of state, actions, rewards, next states, and so on. Okay. But how are we going to simulate? So there has to be some actions that somebody has to take, right? To get to decide this, and the opponent has to decide something. It's not shown here, but the opponent has to decide an action as well, and then intermediate rewards you may not get in the board game of Go, but so somebody has to decide that. So how do we do that? So let's actually use a simulation policy part. Okay. Which means that now I need to also have access to a simulation policy. Just think of the simulation policy as some default program. It's not the best policy, but it's some policy which does something somewhat intelligently. Okay, so if you code up like if then else rule, some hand engineered policy, just think of that as a simulation policy. Okay, so using the simulation policy, you can get a sequence. Okay, you can get a sequence of a trajectory of the search tree, right? Given this policy and the MDP are basically on the environment. Okay, and you can do that for each action. So for each action, you can get this k episodes. K episodes just think of I'm in the starting state ST. I take the first, I have let's say 3 actions. I take the first action, and then take a default policy, somewhat intelligent policy, and keep playing, okay, in my imagination or on the computer, I'll get some quality, get a sense of how good the quality of that action is. And similarly, I can do that for the other two actions. And then and what is that quality metric? It's exactly the Q value function. So for each action, if I take k episodes or k experiences or k paths in the search tree, then I can just take the average, okay, of the returns for each of the returns on each of the experiences or each of the return on each of the episodes. I can take an average of them. That gives me a sense of quality of that action. And then let's just take the action that maximizes that Q function. Okay, so we're just making a Q function sorry, not Q function, but just the Q scores for just the starting state ST. Okay, in this simple Monte Carlo search. So actually, I think actually on this slide I was mentioning, I'm just describing an initial algorithm, okay, called simple Monte Carlo search, or just Monte Carlo search, or just what do you call it, Monte Carlo rollouts. And basically the idea is that you somehow access a simulation policy. And then if you have, let's say, 3 actions to take in starting from the state, okay, you have 3 choices, which choice to make. For each action, you just create about capital K number of experiences or episodes or basically paths in the search tree. Get a sense of how good each action is, which is just the average return. And whichever action gave you the highest return, just pick that. Okay, that's the algorithm here. This is an algorithm for this is pretty much a complete algorithm for the forward search problem. Okay, but you can see that this is quite inefficient because I'm doing maybe some action is really terrible, but even for that action, I'm spending k episodes or k experiences, right? K paths in the search tree. So you want to kind of not waste those episodes, okay? And so again, it comes back to the idea of like something like multi-on Bannet here, where you dynamically change the actions that you take rather than for each action taking a fixed number of episodes. Okay. Any questions about the simple Monte Carlo search? Okay. So here's a visualization. So basically, you're in current position, board state something. Let's say you take action, you take an action A. Okay, so you took an action A. And from that action onwards, you're gonna, in this example, there, K is equal to 4. So you can just simulate 4 times what's gonna happen. How are you gonna simulate? You need to have access to a simulation policy. And where do you have access to that? Some default policy. I mean, one example simulation policy is do random things. Okay, you do random things. So you randomly place a stone, the opponent, you assume that the opponent is also going to randomly place a stone and so on, and eventually see who covers the most territory or who won. And then maybe, for this action, given the behavior policy or given the, simulation policy, you see that you can win 2 out of 4 times. Then that's a score for this action. And similarly, you can do that for some other action, you get a score and get the best one, okay? Here, I wrote the value function here, but you can, so value function is just the max over whichever action is the best. Okay, so I just go back to this. Okay, I didn't write it here, but V of S is just max over A of Q of S comma A. So I'm saying how to compute Q of S comma A here, right? When given that, you can compute V of S. Okay, now let's talk about the key idea in in AlphaGo and all the subsequent models by, for example, DeepMind, including AlphaZero and AlphaGo Zero and so on. So the key idea is something called Monte Carlo tree search. And what is the purpose of introducing Monte Carlo tree search? Is to improve on Monte Carlo search. What is the improvement on Monte Carlo search? Is the idea that if some actions seem bad, then you should not go down. You should not do the K episodes for those actions. Okay, you should try to zoom into those subset of actions which are the most promising. As let's say your evaluation budget is, let's say there are 3 actions and K is 20. Then your evaluation budget is about 60 experiences, right? 60 trajectories in that search tree. Whether instead of spending 20 trajectories per action, you want to kind of dynamically choose those actions which are more promising. Let's say that one of the actions is quite bad, then you should spend these 60 trajectories, most of them on action 1 and action 2, let's say the 2 promising actions. That's the idea. So how do you do that? So the idea is to introduce basically a different policy, a policy which is improving over these experiences. That's these is improving during your search. Okay, a policy that's improving during your search in certain part of the search. In certain part of the search tree. Remember, so when I'm saying search tree, by the way, it's just the tree of everything that can happen from your starting state. Okay, ST. You do something, your opponent does something, you went to some other state board of the, say the board. You do something, opponent does something, you go to somewhere else, and so on, all the way to terminal state. So search tree is everything that can happen. Okay. Monte Carlo tree search is just saying in the search tree, I'm going to somehow partition the search tree into 2 parts, where and the part that is important to us is the part which includes the root or the state ST, where I'm going to do a somewhat intelligent search. Okay, and so the search is going to be I'm going to use a different policy. Okay, so let's call it pi tree. Okay, it's called a tree policy. And outside that region, outside this initial this boundary, I'm just going to use some default policy, just like the simulation policy that we were talking about when we looked at Monte Carlo search. Okay, so outside it's just some default. It could be that random policy, for example. Okay, and this tree policy is going to be somewhat intelligent. This is the one where if we see that one of the actions is quite terrible, then we'll kind of not go down those trajectories. We kind of try to dynamically say, oh, next time we should go down the more promising actions. Okay, so what's the idea? So let's say you are in the current state. Okay, you do one rollout, one trajectory. You evaluate one trajectory. You do something, the opponent does something. Because you're this is the current state, you just do some default policy. Okay, because right now the tree search, the region where you can do something, or where you can improve the policy is just the single node, so you can't do much. So there's no tree policy. You just do something default. Okay, so maybe you won. Okay, now the next time, now you start focusing on increasing your increasing the region which is covered by your tree policy. Okay, so the next time you're gonna pick a action. So let's say in this state there are 2 actions. Okay, so you pick action 1, and then you include that whichever state you get to. Okay, so you include that state action pair. Sorry, it's action 1 and starting state into your search trees, the tree policy region partition, and then from there onwards, this is the default policy. Okay. Now, similarly, you take action 2 and starting state. Okay, which is let's say the second action. Include that in your the partition that involves tree policy, and they take default action elsewhere. Okay. Now, so what we've done so far is the following, right? So we are at state ST. Let's say there are action A1 and A2. So, initially ST, in this state, there was no tree policy and all that. Let's just do a default policy. That was the first slide there. Okay. The next slide, since we didn't, let's explore action A1. Okay. And include ST and A1 into our tree, into our tree partition. Similarly, we'll include action A2 and ST into our tree partition. Okay, the next time. So 2 rollouts. So we have done 3 rollouts so far, right? So you can see 3 in the denominator there. Now what we're going to do is, once we have this, the next time when you do a rollout, which means that next time I want to get an experience, right? So remember, experience is just one trajectory I need to evaluate. The next time I want to do that, I since I've done A1 and A2 once, so let's say A1 picked up 0 out of the so let's say, because by default I did an initial rollout of initial rollout, so 0 out of 2, and then A2 is 1 out of 2. Okay, actually let's just say 1 out of 1. So one rollout which went through A2 and one rollout which went through A1. So I got, so in the sense that I did A2 and then did something using a default policy, I got some reward, okay, which is that maybe I won here and I did not win here. I lost here. And so this is the value. So then the third time I want to do a rollout, or basically simulate what's going to happen all the way to the end, I'm going to prefer A2. Okay, that's the key idea here. Okay, so that's what I meant by a tree policy. Just like in multi-on banners, where I was preferring when we were preferring certain actions which are more promising, right? By keeping track of, think of the UCB algorithm, for example, by keeping track of the empirical means of the reward so far, and adding a bonus term for if some actions are less explored. Similarly, the same idea. You keep empirical performance measures of how each action is, how promising each action is, and maybe add a bonus term for if some action has not been tried much. But that somehow dynamically helps you allocate your 60 simulation or 60 trajectory budget to those actions which are most promising. Okay, that's the idea of Monte Carlo research. So you can see, for example, here, given that the action on the left is more promising, the next time we try action on the left, okay, and the next time after that we still try action on the left, but then we try action which has not been explored. Let's say from this state action pair, you went to another state where there are two actions. So you try the first action, you try the second action, and then here again you can go to those trajectories. Maybe this one is better. So in the next time you go down this path, okay, with more probability than going down useless things which are not useful. Okay, so basically you're zooming into the right sequence of actions. Okay. Okay, so let's see. Okay, so let me actually.
Isn't it kind of analogous to the decision tree model?
Here it's called a search tree. Okay, so it's you're in starting state S. Okay, you take action A1, A2, let's say, and so let's say the intermediate. Let me just put intermediate nodes as dark colors. It just mean ST and A2, and ST and A1, and then from here maybe you went to. Let's say there are only two states that are possible. So maybe new state S1 and S2. Or maybe here also you went to some S3 and S4. Okay. This is a search tree. It's not really a decision tree, but basically each white cell here is actually the state of the environment, or in our case, it's going to be the state of the board. Okay. So this is the board. You took put a stone somewhere. Let's say in the game of Go. This is a new state. Okay.
Okay.
I mean, I only showed two states because maybe there's some stochasticity in the environment. It's not if it's not the game of Go, you could potentially lay in somewhere else. Okay.
Okay, got it. Yeah. I
so it's a different tree.
Yeah, I see.
But the idea is, so Monte Carlo tree search. Just to give up the key idea now, and I'm going to revisit it early next class. And the key idea is that in Monte Carlo search, what you do is if there are only two actions, A1 and A2, and let's say you have a budget of 40 times you can run the whole thing till the game ends. Then you'll say, oh, since I can run it 40 times, let me run 20 experiences. Let me get 20 experiences for A1, 20 experiences for A2. When I say experiences, I'm saying, oh, you try A1, then there's some state ST, A1, right? So that pair. From there you went to S1, and you draw all the way till the game ends. Maybe you won, right? So you do something, the opponent does something, you do something else, the opponent does something else, and so on. So think of all those things. So how are you going to do this? Using some policy called pi simulation or pi default. Okay. Just say you have access to that. So you'll do 20 experiences, and so 20 experiences will go all the way till here. And that will give you a sense of whether A1 is better or A2 is better, right? For example, if I do 20 simulations or 20 runs with A1 and all the times I won, and A2, I did 20 simulations and there are only 50% of the times I won, then A1 is more promising, right?
Right.
To take now, because every time I tried A1, I always won. Okay, so that's Monte Carlo search. Now, the idea behind Monte Carlo tree search is that why should I waste 20 say experiences for A2 if I'm already getting an initial feedback? Let's say I do 2 or 3 simulations there and I already get a feedback that A2 you're not winning at all. Okay, then I should be spending more time on A1. Okay, but if there are only 2 options, it's kind of not that interesting. Let's say you had 10 actions, right? Then if there's some action which is like really bad, you should not be spending going down those trajectories at all, right? That actions experiences can be more towards the more promising actions. Okay, so you can instead of trying out action 10, which is like quite bad, you can try out action 1 or 2. Maybe those are the ones better than 10th one, but you don't know which one is better, so you want to try out a trajectory which includes those actions. Okay, so that's what Monte Carlo research is doing. Yeah, I think what I'll do is, because we're running out of time, I will revisit it early next week. Next time we discuss. Let me at least explain this slide. This is the slide. Okay, so Monte Carlo tree search, as I said, all the complication is in here. So if you think of this as a search tree, Monte Carlo tree search is going to maintain what is called a tree policy. Okay, it's going to maintain a tree policy. Now, this region is not the tree policy. That's just a part of the search tree. What I'm saying is inside this shaded dashed region, you're gonna use a policy which is different from these guys. So it's going to be different from these guys. Outside that dashed region, outside that partition, you're going to just use some simulator. So you're going to just use some default policy. Okay, maybe it's just a random policy. Put a stone randomly on the board, or move up a random pawn on the chessboard, or whatever it is. Okay, this policy is going to be outside that region, but inside that region, I can maintain essentially at each black node a queue of that state and action. Okay, so this region is going to expand over time, over simulations, and within that region, I'm always going to maintain queue values, and then do a more. I'm going to make decisions on which side to go, because I said if something is more promising, the queue values will be higher, and so I'm going to use those queue values to determine, and that using the queue values is essentially what tree policy does. To determine which direction to go, because once I get to the boundary of this, I don't know which direction to go, so I'm just going to use a default policy. But till the boundary, I have queue values, and therefore that queue values are going to determine which direction to go. Instead of doing a very dumb, like a breadth, a very dumb way of trying out everything with equal likelihood, or trying out everything one after the other in round robin fashion, I'm going to go down the most promising routes in the search, more promising paths in the search tree, but I'm going to use queue values. Okay, that's because I'm going to use queue values, and they're going to change over every, because I can update the queue values, and they can change over episode to episode, or every time I do an evaluation. That's why the tree policy changes. Okay, so that's why it's called a tree policy, and that's the key ingredient in a Monte Carlo research. It's just trying to be more efficient with the number of experiences that I'm willing to afford to figure out what's the best action at this current root state ST. Okay. So let me stop here. If you have questions, please let me know. Okay, so let's stop here. I'm gonna revisit AlphaGo. So AlphaGo uses MCTS and then use deep learning. Anyway, next time we're gonna revisit transformers and things like that in NLP. So, but in the first few minutes, I'm gonna discuss AlphaGo zeros. AlphaGo version from 2016. The use of deep learning in that version. Okay. So thanks everyone.